assumption, that is we require random data. So if you have a small sample where you have to satisfy an assumption of randomness, you can use this one sample runs test in order to check whether your sample is a random sample or not, right? So let's see how we are going to conduct this test. So as for an example, you can see you have a few values here, 21, 23, 24, likewise. So if you are going to conduct the one sample runs test in order to check the randomness, the first step that you have to do is you have to take your data set as it is. That is, we are not going to arrange your data set in ascending or descending order. You have to take it as it is. And then what you have to do is you have to denote each observation by a positive plus sign if that observation is more than the previous observation, or you have to denote it using a negative or a minus sign if it is less than the previous observation. So I'll just take this set, right? So I'll just paste it here. Now for an example, if you take 21, when you are running this one sample runs test, there is no sign for the first observation because we don't have a previous observation for the first one. So we have to start from the second observation in this case. So therefore we are going to the second observation, 23. So the previous observation is 21. So 23 is larger than 21. So we denote a plus sign there. And then we are going to the next observation, that is 24, that is larger than 23. So we denote a positive sign. Then we have 27, which is larger than the previous one. So we are going to mark plus sign. Then we have 30, which is larger than 27. So we denote a plus sign. And then we have 28, which is larger than which is less than 30, so we are going to enter a minus mark. Then you have 27, which is less than 28, so you have to denote it with the minus sign. Then you have 26, right, where 26 is also less than 27, so you denote with the minus mark. Then you have 25, which is less than 26, a minus mark. Then you have 23, which is less than 25, minus mark. Then you have 22, which is less than 23. Then you have to put minus mark. 21, which is less than 22. So you have to denote it with the minus mark. Likewise, you take the data set and start from the second observation. If the observation is greater than the previous one, you put a positive sign. If not, you have to put a minus sign. Alright, so let's take this data set. You can see in this table you have a data set. We want to check whether this is a random sample or not. So can you take few minutes and put the positive and minus signs in the second row? Right, so I'll start from the second observation, 22, that is less than 25, so I'm going to put a minus sign. And then I have 27, which is larger than 22, I put a positive sign. Then 23, which is less than 27, minus. 27 greater than 23 plus 28 greater than 23 plus 21 less than 28 minus 26 greater than 21 plus 23 less than 26 minus 30 less greater than 23 plus 21 less than 30 minus 24 greater than 21 plus. So once you put these positives and negatives, then what you have to do is then you have to see how many sets of positives and negatives are there in your sample. For an example, if you look the very first example, here you have a set of positives, one set, and then here you have a set of negatives. So according to this sample, you have two runs here. We take a similar set of signs as one run. So here we can see you have positive set of signs, so that is a 1 run. Here you have a set of negative signs, we take it as another run. So according to this one, you have 2 runs. But if you take this example which we did here, so you can see here you have only 1 negative sign, so we take it as a 1 run. And then here again you have a positive sign again, so you have 2 runs. This is the second run. So you here have another negative sign, that is the third run. And here you have 2 positives, so these 2 we have to take as the 4th run. These 2 observations, they belong to the 4th run. And then 21, that is minus, only 1 minus figure, so you take it as the 5th run, right? And then again a positive 1, you take it as the 6th run. Then again a negative 1, 7th run. Again a positive 1, 8th. Again a negative 1, 9th. Again a positive 1, 10th. So you can see when you take the signs, the consecutive signs, the consecutive same sign as a group or as a run, here you have 10 runs according to this example. So if you are running the one sample runs test to check the randomness, that is the first thing that you have to do, right? So actually there are some problems in this. Now when you check your data set, if you observe too many runs, right, that is actually your data set is not random, because when you have too many runs, it's like your data set is showing a zigzag pattern, right? In the other hand, if you have too few runs, that is, there is a persistency in your data set, right? So there are some difficulties when you have to face when you are running this runs test. Anyway, the assumption of this runs test is the data available for analysis consists of a sequence of sample values recorded in the order of their occurrence. That's why I told you when you get the data set, you cannot arrange your data set in ascending or descending order. You have to take your data set as it is recorded, right? As it is you have to take, and then you have to check for these number of runs, because if you change the order, then we can't say whether it's a random sample or not, because you have changed the order of occurrence. So you have to keep the occurrence as it is and take your data set when you perform the runs test. So here the hypothesis that we wish to test is the sequence of sample values is random against the sequence of sample values is not random. So this is a two-sided test. So as I explained you, when you take the sample, after counting the number of runs you have inside the sample, you take it as the test statistic. So if you take this example, since you have 10 runs, right, our test statistic value here is equal to 10, right? So you can very easily calculate the test statistic. And in this case, when you have to take the decision, what we do is we read the runs table where you have 2 values in the runs table. And when you take from the runs table, you will get a lower bound and an upper bound, right? So let's say the lower bound value is, let's say, RL, and the upper bound value is RU, right? So what we have to do is we have to check our test statistic value is in between these 2 values, right? If our test statistic is in between these 2 values, we do not have to reject H naught, right? That is, do not reject H naught if our test statistic is lying in between these 2 values, right? If not, we can reject H naught, right? So if what will happen if you have tied values, let's say when you check for the observation, this observation is equal to the previous observation. So if that is the case, we have to put 0 there, and then when we calculate the number of runs, we have to just omit that observation. and then we can omit that observation and calculate the number of runs we have, right? So for an example, if you take this data set, okay, now let's say here this is equal to 22. So 22 is similar to 22. So in this case, instead of plus, you have to put 0 and then you have to omit this observation. So if you omit this observation, what will happen here is I will highlight. So you have two negatives. So you have to take these two negatives as a one run. So in this case, these two negatives would, you can mark these two negatives as a one run, right? So likewise, you can omit that data point and adjust your sample size accordingly if you have tight values. And also, as for the Wilcoxon test and for the sign test, if you have a large sample where your sample size is greater than 25, you can use these equations, right, in order to use the large sample approximation. That is, if you can, by using this mean value and variance, you can convert your sample into a normal approximation. Right, so we'll conduct this examples and see. So in this case, it says the following are the bold glucose, the following are the blood glucose levels of 12 patients who attend to a hospital. You have to test at 0.05 level of significance whether the sequence is random. So what is the first step that you have to do? You have to check the number of runs. So I will mark the positives and negatives. So 99 is greater than 86 plus 98 less than 99 minus 90 is less than 98 minus 109 is greater than 90 plus 101 is less than 109 minus 100 is less than 101 minus 110 is greater than 100 plus, then you have 110, the same observation, so you mark it as 0, and 93 less than 110 minus, this is 108 greater than 93 plus 120 greater than 108 plus. So I have marked all the positive and negative values. So let's see how many runs you have here. So here you have a positive value, right? And then here you have two negatives, right? I'll mark it using another color, two negatives, that is another run. Again you have a positive, right? And then again you have two negatives, that is again another run. And then you have a positive, and if you omit 0, you have negative. That is, you can take this one as one run, and then you can take this one as a one run, and then finally you have two positives. You can take these two as another run, right? So let's count the number of runs you have. 1, 2, 3, 4, 5, 6, 7. Right? So you have 7 runs in your sample. So now you have done the calculations. You have calculated the number of runs you have here. Right? So what you can do is, first we can write down the hypothesis. Right, so I'm going to write down H naught. What is the H naught value? The sequence is random. You can write the sequence is random. I'll write it here. H naught is the sequence is random, right? Where H1 is the sequence is not random. Right, so now this is our hypothesis and we have calculated the test statistic R. So how many runs we have? 1, 2, 3, 4, 5, 6, 7. So test statistic value is 7. We have calculated the number of runs. Now we have to read the runs table. So when you read the runs table, what we have to do is, now here when you take your data set, first I'll show you the runs table here. Yeah, this is the runs table. So you have M value and a N value, right? So you can see given in the tables are various critical values for the runs for each values of M and N less than or equal to 20. For the one sample runs test, any observed value of R which is less than or equal to the smaller value or is greater than or equal to the larger value in a pair is significant at 0.05 level. So what you have to do is, when you take this table, now first you have to look at your data set. So you have two values M and N, right? You have two values M and N. So M value you have to take, when you take the data set, what is the first sign you have here? Now according to this data set, you have the positive sign. So you count how many positive signs are there in your data set. 1, 2, 3, 4, 5. According to this data set, I have 5 positive signs, right? And then what can I do? I can count the number of negative signs I have in the data set. So in this case, I'll take negative signs as N. So you have 1, 2, 3, 4, 5. Right? So you have 5 positives and 5 negatives. So in that case, you can read M value is 5 and N value is also 5. So you can hit here 2, 3, 4, 5. So as for your example, the two values that we can read from the table is 2 and 10. These are the two values that we can read from the table, because from this side we read the M value is 5 and the N value is also 5. So at the intersection point you have this value, that is 2 and 10. So that is as the lower bound, and the upper bound we can take the lower bound value we can take as 2 and the upper bound value we can take as 10. So we can see 7 is in between 2 and 10. So that is, we cannot reject. We do not have enough evidence to reject H naught, right? We do not have enough evidence to reject H naught. That is, we can conclude that our sequence is random. So it's very easy to conduct the one sample runs test, right? So I hope that is clear with you all. So there's another example. You can give it a try with the table and see whether this sample is random or not. Okay. And now we are going to discuss another test which is known as so far all the testing procedures that we have discussed, we have applied only to one sample, but as in parametric we have some testing procedures in non-parametric also where you can apply for 2 samples, right? So this test you can apply for 2 independent samples. That is very important. So actually this is when you compare the parametric methods and the non-parametric methods, you can replace the unpaired t-test with this Mann-Whitney U test. Then you have less number of observations. So what we do is, when you have 2 samples, in order to test whether the 2 populations are equal, or in other words, whether the 2 samples are coming from the same population, you can use this Mann-Whitney U test. So our hypothesis of interest is the 2 populations are equal That is our H0 and H1 is the two populations are not equal. So the test statistic for the Mann-Whitney test, you can see we are going to calculate two values as U1 and U2. And what we do is by using our data set, we calculate U1 and we calculate U2. And as our test statistic, what we do is we take the smaller value from these two. Right, I will explain you using an example. So if you look at this, these two equations, you have N1, N2. So N1 is the sample size of the first sample, N2 is the sample size of the second sample. And if you take R1 is what we are doing is we take the summations of the ranks of the first sample, and R2 is the summation of the ranks of the second sample, right? So let's see how can we conduct this test, right? Let's have a look on this. So if you look at example 5.1, it says, consider a phase 2 clinical trial designed to investigate the effectiveness of a new drug to reduce symptoms of asthma in children. A total of 10 participants are randomized to receive either the new drug or a placebo. Participants are asked to record the number of episodes of shortness of breath over a 1 week period following receipt of the assigned treatment. The data are shown below. So what you have to do now, they are doing a clinical trial in order to check the effectiveness of a new drug which is used for the asthma, which is used for children who are having asthma. So they have selected 10 children and they have given the new drug for 5 and a placebo for another 5. And then they have asked the patients to record the number of episodes that they come up with shortness of breath within a week, and the values are given. For an example, if you take this first observation, that is for this patient is given with the new drug, and within the week this patient has come up with 3 times with shortness of breath. Right? So we want to check whether there's a difference between the patients who have used the new drug, right? Or there is no difference. So since these are independent samples, right? No relationship. We have not taken the same patient, 2 different patients. There are 5 set of patients who have used the placebo, and there are 5 set of patients who have use the new drug. So there is no connection. So these are 2 independent samples, and we want to check whether these are the same or not. If we want to check whether there is an effect from the new drug, in other words, we can check whether these are the same or not, right? So using the Mann-Whitney test, we can test it. So the first thing is we can write the hypothesis, that is the 2 populations are equal and the 2 populations are not equal. So what we are going to do is, when you are going to do the calculation, right? So what we are going to do here is, you can see, now these are the values of the patients who have given with the placebo, and these are the values of the patients who are given with the new drug. So the easiest way is, when we take these original results, before we apply the rankings, it's easy if we just ordered our test. So in other words, if you write the 2 set of samples in ascending order. So you can see, if you take this new drug, right, here you can, if you arrange these values in ascending order, you have the smallest as 1, 2, 3, 4, the 5 is missing, then you have 6. So here I have placed it 1, 2, 3, 4, 5 is missing, 6. Where you come to this sample, right, the placebo one, you have the minimum as 4. So 4, 5, 6, 7, and then you have 12, right? So you can write 4, 5, 6, 7, 12. Now when you write it in this manner, you can clearly see the tide values. If you have any tide values, you can clearly see that, right? See, when you take this these two samples, here in the first sample also you have 4, in the second sample also you have 4. In the first sample also you have 6, and in the second sample also you have 6. So it's easy for us to give the ranks, right? So let's give the ranks. Now when you're given the ranks also, you can just divide the rankings into 2 groups and give. Then we can just take the summation of the ranks of the 2 samples easily, right? Now since the minimum of all these values is 1, that is coming from the new drug, we can give the rank as 1 to that. Then the next minimum is 2, the rank is 2. Next minimum is 3, rank is 3. And then we have 2 4s. So for one 4 we can give the rank as 4. The second 4 we can give the rank as 5. So we have to take the mean value. 4 plus 5 divided by 2 is 4.5. So for this observation the rank is 4.5. For this observation rank is 4.5. The next minimum value is 5. So we have used ranks up to 5. So this one's rank should be 6. Then you have 2 6 values. So you can give the rank as 7 and 8. So when you take the mean, that is 7.5, 7.5. So we have used the ranks up to 8. So you can give this as 9 and the last one as 10. Okay. So if you take this placebo group as the first sample, now you can take the summation of these ranks. So in this case, if you take the summation of 4.5 plus 6 plus 7.5 plus 9 plus 10, right? That is the summation of the ranks of the first sample. That is 4.5 plus 6 plus 7.5 plus 9 plus 10. So that would be equal to, if you take the summation, that is equal to 37. Likewise, if you take the summation of the ranks of the second sample, that is 1 plus 2 plus 3 plus 4.5 plus 7.5. Right? 1 plus 2 plus 3 plus 4.5 plus 7.5. So that is equal to 18. Now you can calculate the U1 value and the U2 value. Right? Here I have given with the equation, right? You can see U1 is equal to N1 plus N2 plus N1 into N plus 1 divided by 2 minus R1. You can substitute. So in both samples 1, 2, 3, 4, 5, you have 5 values, right? In the first sample you have 5. So in N1 is equal to right, N1 is equal to 5, where if you take N2 is also equal to 5. So if you substitute the values, N1 into N2 is 5 into 5, right? Plus N1 into N1 plus 1 over 2. Right? This is the equation. So here N1 is 5 into N1 plus 1 is 6. Divide by 2, and then from the whole thing you have to subtract R1. So in our case R1 is minus 37, right? So likewise we can calculate U2 as well. So U2 is N1 into N2, that is 5 into 5 plus N2, that is again 5 into N2 plus that 1, that is 6, divide by 2, and from the whole thing you have to subtract R2. Here it's equal to 18. Right, so in this case we have here as U1, here we have 25 and 5 into 6 is 30. 30 divided by 2 is 15. So 25 plus 15 minus 37, that is U1, you can calculate as 3. And if you calculate U2 value, right, that is again 5 into 5 is 25. 25 plus 15 is 40. 40 minus 18 is 22. So as the test statistic Q, you have to take the minimum out of U1 and U2. Minimum out of U1 and U2. Where in this case, when you take the minimum out of 3 and 22, it's equal to 3. So we have written the hypothesis and we have done the calculations. So the minimum value is equal to 3. Right? So the minimum value is equal to 3. Okay, now we have to, in order to get the conclusion, right? What we have to do is we have to read the value from the critical value from the table. So I'll show you the table. Right, so this is the table. So you have the N1 and N2 values. Now in our case, N1 is 5 and N2 is also 5. And our alpha value is 0.05. So when you check the values, right, here you can see for our test, for our two samples, the corresponding critical value is equal to 2. Right, so you have all these values here in the table. Right, so we can take table value is equal to 2. Right, so I'll just pause my video for seconds, right, because you can see the second example here which I have given. So same method that you have to use, right? You have two independent samples, and then in order to test whether these two independent samples are coming from the same population, you can conduct the test as I explained you, right? So in this case, you can use the same process. So you can take a couple of minutes and just check whether there is a difference between these two groups or not. So I'll give you some time. Just check it and see. Right? Okay, so I think you are able to calculate the table for this example as well, and then you can find the test statistic, that is the value for U, and also then you can find the table value from the table. So after finding the table value, the next important task is how to take your decision, right? So how are you going to take the decision? You can reject H naught if our test statistic is less than or equal to, the table value. So if you look at this example where we have done the calculations, our test statistic is 3, where the table value is 2. So our test statistic is greater than table value, so that is we cannot reject. So according to this example, we do not have enough evidence to reject H naught, right? So that is, we can conclude that both samples are coming from the same population. The two populations are equal, right? So that's how we conduct the Mann-Whitney test. The same thing you can apply for this example and see. And also you can use the large sample approximation. That is, you can go with the normal approximation when you have a large sample here. For that you can use, in this case, if you just look at the table, the critical value table, you can see in the Mann-Whitney table, you have only the observations up to 20. That is, if you have a data set where you have more than 20 observations, then you can go ahead with the large sample approximation. And in this case, we know when you convert our the random variable into standard normal, we have to subtract the mean and divide by standard deviation. So the mean, you can take the mean value as N1, that is the sample size of first sample, N2 is the sample size of the second sample, divide by 2. And the standard deviation N1 into N2, N1 plus N2 plus 1 over 12. Square root, that is the standard deviation. So all the values, when you have the data set, you can calculate the mean and the standard deviation. Plus, if you have tied values when you are calculating, now in this example that we did, we had tied values. Here you have 2 4s, right, and 2 6 values. Remember when we were discussing the Wilcoxon test, how did we calculate the t value for the tied values? Exactly using that procedure. You can calculate the t values and do a small adjustment for the standard deviation when you have tied values. And with the use of these equations, you can apply the one sample. You can apply the large sample approximation when you have a sample which exceeds 20 observations with the Mann-Whitney test, right? So you can just give a try for these examples, right? There is one example in the runs test and another example in the Mann-Whitney test, and see whether you can do the test alone, you can perform it alone and get the conclusions, right? So we will discuss more testing methods from our next session. So thank you so much.